In the last video, we talked about a demand-based construction of sigma algebra. The main idea is this: we have a set S and then we have certain sets that we really want to work with. So we want a sigma algebra which contains these sets, and it may contain other things, but we want to keep the sigma algebra as small as possible, subject to the fact that these sets must be there. So let's work out a very simple example where I need only these two sets, other than of course the entire set. Since sigma algebra must be closed under intersection, so clearly this set must be here. So under complementation it is closed, so the outside is there. So it should not be very difficult to see that if I consider these four sets, then all the sets that we can construct by taking union of these four will actually constitute a sigma algebra. So that is quite easy to check. Now if I just call these things A1, A2, A3 and A4, so anything of the form union of the AIs. Now this construction is sometimes referred to as the partition induced by the sets, because these four things will actually constitute a partition, namely they will cover the entire space and they have no overlap. And sometimes each of these individual four sets is called an atomic set. Thus, this set is an atomic set, this is another atomic set, this is the third atomic set, and the outside is the fourth atomic set. Atomic because you are not going to split this in your sigma algebra. In this example, we had started with only two sets, and this same procedure can be used for any finite number of sets. But if you start with infinite number of sets, then unfortunately this technique will not work, because there are so many possible different intersections and so many atomic sets, so that if you just write it as an algorithm, so you first take all the intersections, then you take all the unions. In that case, you will see that there is no a priori guarantee that the process will terminate. So there we have to use a different way of attack. For this result will be very useful. It is absolutely trivial to prove this, that if over the same set S we take two sigma algebras, then their intersection must again be a sigma algebra. The proof goes like this, very simple. Suppose I take some set A which is in the intersection, which means it is in both script F1 and in script F2. Since it is in script F1, so a complement must also be in script F1. Since it is in script F2, a complement is also in script F2, which means a complement must be again in script F1 intersection script F2. The same thing holds for union and intersection. Once we have this result, now we can talk about the smallest sigma algebra containing a given collection. To understand this, let us start with some collection of subsets of S. And then what we do is we consider the set of all possible sigma algebras containing this collection. Now this collection is definitely non-empty, because if not anything else, at least power set of S, which is a sigma algebra, that definitely contains the collection, because that is the largest thing. Now what we are going to do, we are going to take intersection of all these sigma algebras, and that is again guaranteed to be a sigma algebra. Now you must understand that the proof that I gave you just now, script F1 intersection script F2, that was for only two. So directly it will generalize to any finite intersection, but the same argument holds for any arbitrary intersection as well. So what we shall do is, we shall consider the intersection of all these things. That is again a sigma algebra. By definition, it contains script T, and that also has to be the smallest possible sigma algebra containing D, because if there is something even smaller, then that itself is in this collection. So when you took intersection, how can you get anything larger than that? Now this argument we have already seen when we learned real analysis. There we talked about in R, closure of a set is the smallest closed set containing A, and the precise definition was intersection of all closed sets containing A. And since we knew that arbitrary intersection of closed sets is again closed, so this was also a closed set. That is why we had closure, but we did not have anything called opener, because there we cannot talk about smallest open set containing A. If I take intersection of all open sets, in that case that intersection need not be open. So we use the same technique, except that in place of closed set I worked with sigma algebra. That's all. So just as we had a special term closure, here we have the term generated. So the smallest sigma algebra containing any given collection script D is called the sigma algebra generated by script D, and there are various notations. We shall use this angle bracket notation. So now we are in a position to talk about the demand-based construction. This is precisely what I call the demand-based construction. Your D is that list of demands. These are the sets that I want. Now, in order to make a sigma algebra out of it, you should consider this as the sigma algebra. This is the barest minimum extra sets that you have to include in your list so that the entire thing is a sigma algebra. We have not included anything extra. It is the smallest sigma algebra containing script D. The most important special case of this demand-based approach is, as I have said, the Borel sigma algebra. It is defined like this. For R, you consider the collection of all open sets in R. Then Borel sigma algebra is the sigma algebra generated by script O. Now there is nothing profound about taking open sets. You could have taken closed set. You will still get the same thing because you are just taking complement. You can make life even easier. You can say all open intervals. If you try to generate using all open intervals, again you will actually come to the same things. So there are various equivalent ways of describing Borel sigma algebra. You can make your demand set smaller or larger, but as long as it is rich enough to contain all these open sets, it will always give you the same sigma algebra. That is called Borel sigma algebra. And since I am working with just open sets, so I really do not have to work with R, I can use any topological space and talk about Borel sigma algebra on that topological space. Just consider collection of all open sets on that topological space and the sigma algebra generated by that. And this is by far the most important sigma algebra that is out there.